Hi everyone, welcome to the course Introduction to Soft and Active Matter Systems. Rather, Introduction to Statistical Mechanics in Soft and Active Matter Systems. Hi, I am Divyendu. I'm a Prime Minister's Research Fellow in the Department of Physics at IIT Kanpur, and this course is floated at IEEE's platform. And so we will, go to the details of the course and how you will go through all these steps. So before that, I want to talk about statistical mechanics. So, what is statistical mechanics? So, statistical mechanics is a very important formalism in physics that is used to study any physical properties or of any physical systems in bulk on depending upon the dynamical evolution of microscopic constituents of that systems. And it was this total formalism of statistical mechanics. It is uh, based on the mathematical statistics on one hand, and on the other hand it is based on Hamiltonian mechanics. So which was actually, if you see the trajectory of physics, the history of physics, so this particular tool, statistical mechanics, so this played a crucial role in the advance of physics. And it sort of, in last 100 years, it is a it seems that it has proven to be a fascinating tool. Now, the second thing is soft and active matter systems. So, what are those soft systems? So, if I take some ideas from uh, Nobel laureate Diogenes Nobel lecture, so he first termed it as soft systems are those systems which are easily deformable. So we are basically surrounded in our everyday life by those soft systems, be it some paste, be it some any kind of uh, any kind of paints or otherwise. And also, like, in our bodies, all those cells, how bloods, all those important tissues, they are all part of these soft systems. And what are those active part of, what are the active part of this? That means they are not equilibrium, so they consume energy, or they take energy continuously, or always take consume energy from the environment, and they produces some uh, mechanical forces, or some you know it does some work. So this flow of energy is, there is a arrow of flow of energy in the system. So this is a sort of informal definition of these systems. So basically what we will do, we'll study how we can use different statistical tools to get uh, different physical properties out of those systems. And an important note for this system is, these in recent years, like last 10-15 years, soft and active, specifically active matter systems, got immense attention from physics fraternity, because it has a plethora of you know applications, and it has plethora of systems to be studied, right? Because there are lots of systems if you think about soft and active matter systems. So that is important, so that's why it is useful to study. And also, if you think about like how our why is this, why this course? So because if you see our standard statistical mechanics courses in our graduation or master's level course, so they are since the statistical mechanics tools has plethora of applications, so that they use classical statistical mechanics and quantum statistical mechanics, and they sort of ignore the basis of this software activator systems, which is called Brownian motion. So we will give first importance to study Brownian motion, and often it is neglected in various courses. They do not give that much importance to study Brownian motion in details. So that we will cover here. And basically, since I also do my research in software activator systems, so I thought that it will be useful if I share some of my experiences or some of my learnings through this medium with you. Okay, so let's start. Let me share my screen so that I can start. Just just a So I hope you can see my screen. Okay, so let's start then. Okay, so yeah, so the name of our course is Introduction to Statistical Physics in Soft and Active Matter Systems. Okay, so the module so module number of this course in the ISSS platform is PMRF ISSS 146 2024, and I am Divyendu, instructor Divyendu Mondal, and my PMRF ID is 23 sorry 2301733. Okay, so we will lecture. So we will give about 20 lectures, and duration of the lecture hour will be 1.5 hours. So you can there is a platform, so you can ask different queries there. So, and also you can write to me in this email ID dmondal physics at the dot. Okay, sorry, there's some connections. Okay, so demondelphysics@gmail.com. So you can, you know, ask your queries there, and that's it. So we will cover the whole thing. So this is one kind of a brief introduction to the software and active matter systems and how we can apply statistical mechanics in these systems. This is not complete, okay? So this is an evolving field. You can search in YouTube. There are multiple, conference proceedings or lectures on different, websites. You can refer to the ICTS YouTube channel. There are quite a few, there are numerous, conference or schools about statistical physics, and there are lectures. That is totally based on the how, current researchers are doing on different problems they are solving. And this is this. So let me, start our lecture. Okay. Okay. So first we will understand. So I told you about thermal fluctuations. So first we will see how different random motions is there. So first the first chapter will be, or first discussions will be about Brownian motion and thermal fluctuations. So basically this is a grand topic. We will mostly talk about this. So this will contain 60% or 70%, and in details we will talk about this. And then we will go to the active matter systems. So first, mainly we will talk about a system which is, we will talk about time dependent time dependent, that means it varies, phenomena happening at equilibrium or near equilibrium. Okay, so that we will, that is the main motto of here. And so before that, first, what is equilibrium? We know that equilibrium is a stationary state. That means here it doesn't change with time. So we know that an equilibrium state is a stationary state. That is, it does not vary with time. Okay, that means the macroscopic physical, what does it this means, does not vary in time. So that means actually that macroscopic macroscopic so you will also get all these notes in a drive link. I will send or I'll share it, so you can always download all these notes. So this uh, physical quantities macroscopic physical quantities, that means pressure, concentration, density, these shouldn't depend on time. Should not depend on time. Okay. Okay, so now, so these are macroscopic things. Now what happens, what now my question is, what will happen if we measure this quantity, measure these quantities for smaller systems, for smaller systems. That means if we see what will happen, a general guess will be that their value should fluctuate, their values should fluctuate fluctuate in time. So means if you see, let's say some example, you can see that pressure acting on a cubic box wall, let's say its size is 10 nanometer cube, that actually changes or fluctuates, changes with time. Now why this is happening? Because these are actually happening because of the thermal fluctuations, or these fluctuations are mainly caused by the random thermal motion of molecules which constitute the system. So these fluctuations are caused by random. So there are few loaded words. First is random thermal motion, or thermal motion of molecules constituting the system. So by random means you cannot guess it, right? Means you cannot deterministically say that that will be the change. Now this, in this discussion, most of the times we will talk about that how this time dependence of these fluctuations uh, you know that happens in the system. So basically in our discussion we will talk about these fluctuations as Brownian motion. So in our discussion, in our discussion, these fluctuations are mostly seen as Brownian motion. So we will also see how to implement that. We will talk about it. So Brownian motion. So this is, we will term it as BM. Okay. So in 1905, Einstein, in his three seminal papers, he first talked about special relativity and photoelectric effect and Brownian motion. But the other two papers got that much attention in due course of time. But this uh, Brownian fluctuations paper, or molecular fluctuations, that was groundbreaking at that point of time, because they didn't know about how molecules, is there any existence of molecules, right? The concept of molecules are not that established, but that paper sort of proved it. I think you should guys read the paper once. So Einstein actually showed the manifestation of thermal motions of molecules. So in 1905, Einstein showed the relations of microscopic fluctuations at equilibrium to macroscopic response of the system. To the external forces or external agents. Okay, and this theorem is famously called fluctuation dissipation theorem. So here we will discuss lots of things, but we cannot discuss everything in details. But I will give some, I will start this, and since this is an advanced thing, so you can always read more about this the topics. Okay, and this fluctuation dissipation theorem later you know gave an important leads to an important principle. This is called Onsager principle, which actually gives a common basis in the dynamics of soft matter. Okay. Okay, so let's see what are those thermal fluctuations. Okay. So first, to do this, we will do a certain statistical, you know, tools. We will use certain statistical tools to see, that is time correlation functions. Time correlation functions. So here, let's say, first think about it. A small particles, let's say a size less than or 1 micrometer suspended in a fluid. So fluid molecules are very less. This is and around of Armstrong level. So small, it is small particles, compared to the everyday objects that we see in our naked eyes. But the small particles are large compared to the fluid molecules. Suspended in a fluid, when it is suspended, this will undergo some random irregular motions, because you have this Brownian motion is actually named after biologist Robert Brown. So what he did, he actually suspended few some petals, their seeds in a liquid, and he saw under microscope that they are moving, or they are showing some irregular motions. So they will show it will show it will show irregular motions. Irregular motions. What is irregular motions? Let's say spherical particles changing their position randomly. Changing their positions randomly. This is one kind of irregular motions. And let's say, if you say an asymmetric particle, let's say rod particle. So the rod like particle, rod shaped particles, they are changing their positions and orientation randomly. And these kind of motions are called Brownian motion. This kind of these are called Brownian motion. So there are many more examples. So you'll see also little bit of them in this. So actually, how this Brownian motion is manifesting, that is because it is actually is a manifestation of the thermal motion of the molecules, because since molecules are there and there are, you know, uncountable number of molecules in a fluid, so they actually moves due to the thermal agitation, and they actually strike that small particles, that is this small particles, we call it Brownian particle. So they, since they are colliding with each other incessantly, so that will produce this kind of uh, uh, you know, Brownian motion. So if you see how to do that, how to see that, let's say this is one spherical particle starting from here, go here, 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 again here, again here, 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 here. So this is one kind of Brownian motion. So it starts from here. There is no certain periodicity. Starts from here. Let's say this is x equal to 0. This is x equal to 2. You can see these are zigzag kind of motion. And if you think about a rod-like particles, let's say this one. So it was like this. So this has the directions like this, which is, let's say, u vector of 0, and it it at t the position is like this. So this will be, the vector will be like this. This is ut. So this, so their position is changing also, their orientation is also randomly changing. Okay, so now we will use different statistical, you know, mechanics tools here. Now according to statistical mechanics, according to statistical mechanics, if you see that any particle of mass m, any particle, any particle of mass m placed in an environment of temperature T, temperature capital T, so moves randomly with velocity of order kBT by m. So this is coming from kinetic theory of gases, because if you see, you know, how, so energy will be, you know, distributed in all degrees of freedom by half kBT, the equipartition theorem. There we used to, you know, see that for one this thing, half mv for half mv x square. So this is sort of like this. This was half kBT. So this is a use of equipartition theorem. This were, you know, at graduation level. Okay. So from here you can easily write this. Okay. So now if you see a macroscopic particle, let's say a macroscopic particle or a macroscopic particle, let's say mass is 1 gram and size A around 1 centimeter, then this velocity v is of the order of 1 nanometer per second. So very low, very low, because you can see here as mass increases the velocity will be much lower. Now let us say if you take a colloidal particle, a particle which is suspended in a fluid, doesn't mix with it or doesn't become a single system. So colloidal particle, let us say its size is 1 micrometer. So and its mass m is around 10 to the power minus 12 gram. Now if you see the velocity v, that becomes around 1 millimeter per second. So this is sort of observable at microscope, right? By microscope. Okay. Now those particles which shows Brownian motion are called Brownian particles. So particles undergoing Brownian motions are called Brownian particles. Okay. So let's say if we now measure a certain physical quantity of a Brownian particle. So let's say if we measure position or certain like orientation or anything, orientation angle. So let's say we are measuring certain physical quantities, and these are, let's say, denoted by generalized coordinate system, let's say xi, where I is 1 2 3. Okay. So now what we will see, if we observe their thing, so we will get a sequence of data, right, of xit. We will get a sequence of data, let's say xit. Now this will vary randomly in time. They should vary randomly in time, right? That is what we have seen earlier. Now let's say you repeat this measurement for many systems, similar systems at equilibrium. So now repeat this measurement for many systems at equilibrium. Okay. Now we define a certain average, define the average like this. Okay, 1 2 3. Okay, and this average is called ensemble average. Ensemble average, because here we are doing the average of an ensemble copies, many systems or similar systems at equilibrium. So this kind of average is called ensemble average. Okay, But in some practical scenario, in different experiments, we do this kind of average for a particular system. So this is sort of a time average we will talk about. Okay, now if you see, so now we have so for a Brownian particle, for a Brownian particle for a Brownian particle at equilibrium, this average is independent of time. The average is independent of time, and it is written as xi average. Okay, so which is taken as, this is the third bracket, so xi t. Okay, and this average is independent of time, it is not changing. So let's say this is equation number 1. Now what you will see, now let's calculate the deviation of this xit, individual xit, from this average. So the deviation of xi, so at each instant of time how this variable changes from the average. Let's calculate that. What that will be? So let's say this is denoted as this delta xit. This will be xit at that instant of time minus xi average. Okay, so this is equation number 2. Now let's say, so this is a deviation. Now the correlation, so the correlation, so this I means it is for a certain direction, let's say x, y, or certain along certain directions. So now the correlation of delta xit and delta xjt, so these are for different direction I j, that means different direction. Also this correlation should be calculated at different times, at different times t1 and t2. Let's talk about this. So this is actually denoted as similar average delta xi, let's say t1, delta xj at t2, and their average, and this is called time correlation function. Time correlation function. Now let's say if I and j are same, that means if you calculate this correlation function for the same physical quantity, that is called autocorrelation function. Now if I equals to j, that means correlation for same physical quantity, that means this one delta x I t1, delta x I t2. This is called autocorrelation function. Okay, and if I not equals to j, that means for different physical quantity, if you take different correlation for different physical quantity, this is called cross correlation. So delta x t1, delta x j t2, this is called cross correlation function. Okay. Now at equilibrium, there are some properties of first, at equilibrium, the time correlation function, does not depend on the origin of time. That means where you are starting the time. Because why this is true? I am pausing for 1 second. So please pause that and try to answer it. So it does not depend on origin of time, because there, when it is in equilibrium, it is at steady state. So it does not depend on time. So there, the absolute sense of time is not required. What is important is it depends on the difference of time. Difference of time, which is here in that case t1 minus t2. So if that is the case, then we can easily write following thing. First, delta x I t1, delta xj t2, their average should be delta xi. Let's say now you are just taking t2 minus from both the end, so this will be same thing, because you are just writing this. And also you can change these two fellows in two directions. That means it does not depend whether, since product is commutative, so you can also write that delta xi of 0 and delta xj t1 minus t2, right? So, and this property is called time. This is called time translational invariance. That does mean that time do not have any preferred direction. So here you can see whether you can take start taking this delta xj, that deviation at 0 time, or you can take the other variable at 0 time. So that does not you know that shouldn't change. Now if you say, now if you use this relation, if you use this time in translation invariance relation into this, then you can easily write that delta xi t delta xi 0, because for autocorrelation this is two same things. So now you can easily, you can minus t from those two ends, so this becomes delta xi 0 delta xi minus t. Okay, also you can just now change it, delta xi minus t delta xi 0. So now we can see that autocorrelation function is an even function. So autocorrelation function is an even function. Okay, so what do you mean by this? I mean by this, let's say this one and we want to calculate like this, delta xt delta x0. So I don't want to calculate it right now, but if you see how this changes, this should change like this. Okay, so symmetric around these two, and t this. Okay, okay, okay. So now I will again discuss about some symmetry properties of time correlation function. Okay. Symmetry properties of time correlation function. So Onsager showed that if these xi variables, these quantities are the, so I goes from 1 to whatever the quantities are there, are the quantities representing the particle configuration let's say how particle configuration is, let's say For example, let's say this is position, orientation angle. So if xi's are those quantities or their functions, their functions, how can it be? Let's say dipole moment. It depends on the dipole moment, depends on how it is oriented, right? This dipole moment. So then the cross correlation, the cross correlation of those quantities, cross correlation function of those quantities, cross correlation function also becomes even function of time, even function of time. That is delta xit delta xj0 is equal to delta xi minus t delta xj 0. So this is question 4 and this is question 5. So it is only possible when these quantities are the configurations. This actually they represent the particle configurations. Okay, and this actually derived from a fundamental law of physics. So this is derived from time reversal symmetry in the fluctuations in the fluctuations at equilibrium. So at equilibrium, fluctuations are time reversal symmetry. So how to say that this is time reversal symmetry? Let's say if you capture a video of Brownian motion of a Brownian particle. Now you have captured the video. Now if I show you that video in a reverse mode, then we cannot tell the difference between the forward video and the reverse video. Okay, so that means if we cannot distinguish the forward and reverse video, then we can say that video is taken at equilibrium. That because the if you show the video in reverse mode, then those, like when you are showing the video in reverse mode, that incident is also physically possible. If that event in reverse mode is also physically possible and takes place with the same probability as the event shown in normal mode, then we can say that thing. Okay, now this is a result of the a certain principle of statistical mechanics. Okay, so we will see how. So now from the molecular point of view, from the molecular viewpoint, Brownian motion is deterministic. Why is that? That means if we keep track of every collision of the Brownian particle with the molecules, then it is deterministic. Of course, it is deterministic then. Now, if we see from a molecular point of view, now the catch is if we focus on if we focus on the motion of Brownian particle, which is a resultant of all the molecules colliding with the Brownian particle, then the stochastic nature or the random nature, the stochastic nature comes. Okay. But if we look at the motion of Brownian particle and also the surrounding fluids, both of those things, then this process is deterministic and governed by Hamilton's equation of motion of mechanics. So let's say these are, let's say Q1, Q2, QF and P1, P2. So these are the variables required for Hamiltonian dynamics, PF. These are the set of coordinates and momenta of all particles. All particles, that means the molecules of the fluid and also the Brownian particle. All particles constituting the system. Okay. Now whole set of variables is, let's say we denote the whole set of variables by this sign. So that means if whenever we write this is actually becomes Q1, Q2, QF, P1, P2, PF. Okay. Now Hamiltonian of the system then denoted as Hamiltonian as H of this thing. This is the Hamiltonian of the system. Hamiltonian of the system. Now in the reverse mode, let's say if you take in the reverse mode, then this, let's say if you are now reversing the video, in the reverse mode the position will not change as time t changes to minus t, right? And then in the reverse mode this changes to Q1, Q2, Q3, sorry, Q2, QF minus P1 minus P2 minus PF as the time changes and t changes to minus t. Okay. Now let's say this whole system is denoted as minus omega. Okay. Now since these are equilibrium, since the Hamiltonian will also have the property, Hamiltonian has the property h of omega is equal to h of minus omega. This is the property at equilibrium, right? Because these are states, omega and minus omega are equally possible, right? That means the probability of finding this state and probability of finding this state are same. So state means starting from an initial state reaching to the final state, and starting from the final state reaching to the initial state, that will be in the reverse case. The final state of the original case will be the starting point of the reverse case, and initial point of the original case will be the final point of the reverse case. Okay. So also you can, so this is equally possible, right? Just so basically what you are saying, that probability of finding this initial state and the reverse state are equal. Okay. Okay. And also the time let me write it again. Also time evolution of the normal mode, normal mode means the original mode, and that of the reverse mode, that of reverse mode are both allowed by Hamilton's equations of motion. Equations of motion, right? So what does it mean? It means that, let's say, state omega 1 evolves to state omega 2 at at time t. Okay, so the state minus omega 2 should also, minus means the reverse of this, should arrive to state minus omega 1 at t. So this is the reason of this equation. This is the reason of this equation 5. So if it starts from here at time t, it should, if it starts from state minus omega t, it should reach there. Okay. Okay. Now let's say an observable physical quantity, let's say xi, it is function of xi of that state. Okay. Let's say now we are writing any observable physical quantity xi as a function of, as a function of omega, like this, xi hat omega. Okay, xi hat. Now if omega replaced by minus omega, this function remains unchanged or changes sign. So if omega is replaced by minus omega, the function xi usually remains unchanged. Okay, so therefore you can write like this: xi hat of remains unchanged or remains unchanged or changes sign, because two things can be possible, right? Either it changes or changes sign. So like this should be epsilon I xi of omega. So here if it is changes sign, so epsilon I will be 1 or minus 1. Okay, two possible values, either 1 or minus 1. So that means now for certain variable it does not changes sign. What those quantities are? quantities like quantities like position, energy, this epsilon I is equal to 1. And for quantities like velocity or angular momentum, velocity or angular momentum, epsilon I is minus 1. Why? Let's say it starts from here and goes here. So when you know going from these positions, in in reverse time, these positions do not change time. Sorry, do not change their sign. But let's say from here to here, if the velocity is v, from here to here this velocity will be minus v, right? Because position is not changing, and if you think about velocity as position by time, since time is reversing, it will reverse, right? So now if you use it generally in this expression, then delta xi t delta xj 0, that equals to two things can be happen here. One thing, for this will be epsilon I for this one, and for this one will be epsilon j, and it will be delta xi minus t delta xj 0. So mostly this will be our expression. So now if in that reverse situations it does not change, because from here to here what is happening is it's changing the time. It was from 0t to 0 minus t, the dynamical these things. So mostly in our discussion we will consider mostly our discussion will be involving epsilon I is equal to 1. Now using time invariance, we can write this expression number 7 as delta xi t delta xj 0 is equal to delta xi minus t delta xj 0 is equal to, if you use the commutation relation, delta xj 0 delta xi minus t, and again if you do this time invariance, if you add t to this, sorry, time translational invariance, then this will be delta xj t delta xi 0. This is using time translational invariance. Okay, so that means time correlation function time correlation function delta xi t delta xj0 is symmetric with respect to the exchange of I and j. Okay, so that's this. And for certain quantities, I will just you know stop the discussion by discussing this. So for certain physical quantities, you can think as position of a free Brownian particle. It is not convenient to consider the time correlation function because their averages are not different. Averages are not defined. Because if you see for free particle, if you think about, so it's not convenient delta xi t delta xj0 calculating time correlation function is not convenient because averages xi and xj are not defined. So for this kind of systems, for this kind of systems, it is convenient to calculate the correlation of displacement. Convenient to calculate the correlation of displacement. Okay, so how to calculate that? That is, displacement will be which quantity? So xi t, what is the displacement at time t, right? So we need to calculate the time correlation of this quantity. So that quantity will be xi t minus xi 0 xi xj t minus xj 0, their average. So these functions are related to each other if this delta x0 whole square is finite. Okay, so to correlation functions are related if delta x0 whole square is finite. We'll see in this next discussion, or in this discussion, let's say, so we want to calculate this. So this will be, if you do, so let's say if you do the average, if you deduct the average from here, then here, then here, then here, then you can easily write delta xi t minus delta xi 0 times delta xj t minus delta xj 0. So what we are doing here actually is delta xi 0 is xi 0 minus xi. So in this way we are doing. Okay. So if you do this step, then there will be four terms. So there will be this term xi t x delta xj t minus delta xit delta xj 0 minus delta xi 0 delta xj t plus delta xi 0 delta xj 0. Okay, so this is, let's say, equation number 1. Now if you use those two equations, equation number 5, time reversal symmetry, and this one, the time translation and invariance, if you use these two things, so if we use if we use time translational invariance and time reversal symmetry, then we can write all these two things as this one will be similar to this one, and this guy will be similar to this guy, right? So then we can safely write as this will be 2 times delta x I 0 delta xj 0 delta x I t delta x delta x I t and delta xg 0. Okay, the same thing, because we have just this curly yellow lines, this will be equivalent, this will be similar. So hence the dynamics can be characterized either by the deviation or by the correlation of the dynamics. So here we can easily write dynamics of the fluctuations can be characterized can be characterized either by time correlation function, so which is like TCF, time correlation function of deviation at time, deviation at time, which is denoted as delta xi t as xi t minus xi 0, or by or or by the correlation of displacement. So given if this is finite, that means this guy is finite, then we can write the we then is this these two relations can be, they are related. Okay, so we are stopping here. So we will resume the next discussion in the next class.